Welcome to Chapter 8 Synthesis Practice.
So in Chapter 8 we were primarily focused on addition reactions, which means our starting material would be an alkene. And the things we need to know about alkenes is that they can act as nucleophiles or bases. They're not electrophilic because they don't have a leaving group, but they can be a nucleophile or base. So that's the first thing we identify. Then we look at the conditions we're under. So here we're under HBr conditions. And those of you who've seen HBr before know that HBr is a strong acid. So given the reactivity of starting material and conditions, chances are we're going to have an acid-base reaction happen first. So mechanism-wise, I'm going to show an arrow of the alkene picking up the hydrogen and kicking out a Br-. And because of the nature of an alkene, that means one of the carbons that we're sharing the electrons gain the hydrogen, the other carbon has to have a positive charge because he's now missing an electron. So we have the choice here. We have option A, where we put a carbocation here and a hydrogen there, or option B, where the hydrogen goes there and a carbocation goes there. And one of those is acceptable, the other is not. This guy can't happen because that would be a primary carbocation, so we know we can't form those, which means the alternative is the only option we've got. So that's what happens. We get a carbocation here. We're definitely not done though. Carbocations are still highly reactive. So they're mostly reactive as electrophiles. They're highly electron deficient, so something can attack them. And in the first step of the reaction, we also generated the Br-. Right? We didn't have it to begin with, but once we took off the proton, we now have Br-, which is a very good nucleophile. So, nucleophile attacks electrophile. This is just like your SN1, and he can attack there to give me this as a final product. Now, because this is just like the SN1, we do have to be concerned about stereochem. The carbocation's planar. But the bromine could attack top or bottom and we won't get a different product because that's not a chiral center. So this is the one and only product. And it follows Markovnikov's rule, which we don't have to memorize because if you do the mechanism, you'll see you always get the Markovnikov product due to where the hydrogen has to add to form the more stable carbocation. So this question again, very, very similar. We have an alkene, which can be a nucleophile / base, and we again have HBr, which we know is a strong acid. And an acid is a proton donor, which means this guy has a weak bond to hydrogen. So given the reactivity of what we're starting with, it makes sense we're going to see an acid-base reaction happen first. And again, the question comes up where we have to decide where we're going to put the positive charge and where the hydrogen will go. For clarity, I'm going to show the hydrogens going here. I don't have to show that, but the positive charge goes here, which I do have to show. That's mandatory. So at this point, again, we have a carbocation, which is highly electrophilic, which means my nucleophile can attack, and I generated that nucleophile in the first step in the form of Br-. That's the only thing really nucleophilic kicking around, so it makes sense that's going to be what attacks. So the Br- can attack top or bottom, again, because the carbocation's trigonal planar, but again, in this example, we don't have to worry about stereochem because I do not generate a chiral center. When the Br attacks, we get this product and only this product. Slightly different conditions in this example. We again have an alkene starting material, but we're under sulfuric acid / water conditions. So what this is telling me is that I have dilute aqueous H2SO4. So when H2SO4 and water combine, because H2SO4 is such a strong acid, it will protonate the water, which gives me a hydronium, and HSO4-, the conjugate base of sulfuric acid. So when we carry out the reaction, we really should be focusing on using these two things because the sulfuric acid is no longer really present. It would completely dissociate in the water. We do have extra water kicking around, so if we have to use that in the future, that's perfectly fine. So again, we assess what we have to start off with. We've got a nucleophile / base at the alkene, and then we have a nice strong acid in the form of the hydronium. So strong acid. So, and then we have a weak base over here, not really expecting this to do a whole lot. And we have water, which can be a few things. You can be a nucleophile, a base, or weak acid base. So chances are, again, we're going to have an acid-base reaction happen in the first step. All these reactions are acid catalyzed, the first three that we've shown here. So the likely reactive acid this guy is going to come into contact to would be the hydronium. So nucleophile slash base takes a proton from my hydronium to give me water and a carbocation. So again, we have to assess which one gains the hydrogen and which one gains the positive charge. So in this case, we have two options, this carbon and this carbon. So I'm going to give the hydrogen to the carbon that has the most hydrogens already. I know I'm going to follow Markovnikov. And the reason being because I have to form a carbocation. So it only makes sense that I'll form a secondary carbocation because the only other alternative there would be the primary. So I get my carbocation. As I said, I've also released water in the process of that reaction. You don't really have to show that in the mechanism though. And because we formed a carbocation, something we should assess, that is a secondary carbocation. Anytime we have a secondary carbocation, we have to look out for rearrangements if they're possible. So in this case, I do have the possibility of a rearrangement. I've got 3 methyl groups on the beta carbon adjacent to that carbocation. So I'm going to take one of those methyl groups and give it to that carbocation. So that arrow indicates that both the carbon and the electrons contained in the bond have all moved over to that carbon. So drawing the product from that rearrangement, we have 1, 2, this guy still has 2 carbons, this guy now has another carbon, and that means that the carbon I took the methyl group from is left with a positive charge. So when I did that, we have to assess and make sure this is a reasonable thing to do. In this case, I went from having a secondary carbocation to a tertiary carbocation. So that would be energetically favorable, it's reasonable to make that happen, and we have to assume that would be the major pathway. So now that we have our most stable carbocation, we want to reassess the reactivity. And carbocations, as always, are very strong electrophiles. So because I don't have heat and because I'm under conditions that provide me a lot of nucleophile, good chance this is going to be a nucleophile attacking the electrophile, again like the SN1. So assessing the conditions that I have, I either am going to use water as the nucleophile or HSO4-. The HSO4- is super resonance stabilized, so he's not nucleophilic at all. You're never going to use him as a nucleophile. Water, on the other hand, we have lots of, and once it gets deprotonated after the attack, it's nice and stable. So we're going to use water as a nucleophile in this case. And again, water could attack top or bottom, but once again, I don't have to worry about that because I'm not generating a chiral center. So this does not automatically give me the product. Never skip a step here. If I draw the product of what I did exactly with my arrows, I showed one lone pair making the bond, so this lone pair is now making the bond to the carbon, which means I still have one lone pair left over and a positive charge on the oxygen. Very important you don't miss that positive charge, otherwise you might think that is the final product, but that's still not stable, so we have to take another step here to make it into something more stable. And I've got lots of water kicking around, which means I can use another water molecule to deprotonate this intermediate, which will give me a nice stable product in the form of an alcohol. So this reaction is a Markovnikov addition of water. But you don't have to memorize that just from seeing the conditions. If you work through the way we just did, then you can never go wrong. You'll notice it does the Markovnikov addition, but that means you also have to watch out for a rearrangement. In this example, we did have a rearrangement, so always watch out for those with any of the carbocation intermediates. So for this reaction, our starting material is an alkyne, and we've seen a couple types of reactions with alkynes, primarily addition, which makes sense, we're in chapter 8, but we've also seen reactions where we deprotonate an alkyne and use it as a nucleophile, so just keep that in mind. For this one, it's pretty obvious we're doing an addition reaction. We have the presence of hydrogen here. So H2 means that we're probably doing hydrogenation, adding H2 across the double bond. So the real question is, are we adding multiple equivalents of H2? Are we adding one equivalent? And if we are we adding syn or anti? So to determine that, we have to look at the catalyst that's provided. So in this case, it's Ni2B, which is an example of a poison catalyst, similar to Lindlar palladium. And in this case, what we're going to be doing is a syn addition. And unfortunately, this is one of those mechanisms you just don't see. We didn't actually cover this in my section, which means that we just have to memorize this. So recognizing H2 is important to determine that it is an addition of hydrogen, and then looking at the catalyst determines what type of addition we're going to do. So in this case, because of the catalyst, I know that we're going to be doing a syn addition of H2. So that means the both hydrogens add to the same side of my alkyne. So if that's my alkyne, I'm going to be adding both hydrogens to the same side, which would give me a product that looks like this. Be an alkene with 2 hydrogens down, 1 methyl group up, and a hydrogen on the other side up. In this case, this isn't a cis or trans product because we have 2 of the same groups on the same carbon, but we do have to recognize it's a syn addition to do it properly. So for this reaction, we have an alkene starting material again, which we know can act as a nucleophile / base. And we have Br2 in the presence of dichloromethane. So the key thing to recognize here is the Br2, which if I draw it out, looks like this, with some lone pairs kicking around. And up until this chapter, we really didn't think Br2 was highly reactive, but we came to recognize that there can be a temporary dipole created in the Br2 when it's put in the presence of other electrons. And as soon as that temporary dipole happens, where the electron cloud's shifted towards one side, then one of the bromines becomes an electrophile and the other one becomes a leaving group, which allows me to do some reactivity. And if you see this, nucleophile, electrophile, leaving group, then we're going to do something similar to an SN2. With these ones, we do have to watch out for the solvent. In this case, it's CH2Cl2, which is not reactive. It's not a competing nucleophile, so it's strictly a solvent and won't participate in the reaction in this case. Now, in my opinion, the hardest thing about these types of reactions is the stereochemistry. So I'm going to show you the trick I use to try and make sure that I get the stereochemistry always correct. The first step is to take my planar alkene, which is planar, absolutely, but I'm going to make it into a 3D structure where I have 2 of the groups coming towards me and 2 going away. So basically, try this with your model kit, build that example sample molecule here, and then take it from being planar and rotate it. So 2 of the groups are coming towards you and 2 are going away. And what you'll see is this. So in this case, I'm going to rotate it so that methyl groups are coming towards me, which means the 2 ethyl groups would be going away from me in the back. And you'll see why I do this. I just find it makes it a little bit easier to see the stereochem of the Br2 addition. So, to do the Br2 addition, we have a bromine molecule here. We've identified we have a nucleophile, an electrophile, and a leaving group. So to show that, we have my double bond attack my electrophile. He's going to kick out a leaving group, but in this example, if I were to do that, that would generate a carbocation, which is totally what we did when we did the HBr addition and a bunch of other types of addition. The trick with the bromine is that he's a little bit bigger, no, substantially bigger. He's bigger than hydrogen. He can actually donate back electrons because he's bigger and he has more of them. So instead of actually forming the carbocation, we form the weird 3-membered ring intermediate, the halonium ion. So that means in our mechanism we have to show 2 electrons going back to one of the carbons, doesn't matter which one, to indicate that there will be a 3-membered ring intermediate. So, product of what I'm showing here, I showed the bromine attacking from the bottom of my molecule. You can also show it attacking from the top. So I'm going to do the second one as well. But for now, let's show the carbon bound to the carbon, the bromine at the bottom, and because I've dashed and wedged the other groups, this guy's actually in the plane, which is nice. And the other groups just kind of get pushed back. I'm just going to draw them in bond line. Right? They're still the same. They're still dashed and wedged the exact same as in the intermediate. But it's just pushed up a little bit to make space for the bromine. Now at this point in this intermediate, I recognize that my bromonium ion is still highly reactive. Bromine is not content having a positive charge, so what he's going to be doing is pulling electron density away from the carbons that he's attached to. So although these aren't technically carbocations, they're pretty darn close. They're still losing a lot of electron density to the Br+. So what that makes them is highly electrophilic because the Br over here could act as a leaving group if I were to attack this attack the carbon as an electrophile. These electrons can be broken away to give me a Br neutral. So both carbons are susceptible to attack. In this case, you'll notice that the groups are exactly the same coming off of them, so it doesn't actually matter which one I attack. I'm going to choose to attack from the right one, and when I have the second intermediate as well, I'm going to make sure to do the same thing. So here's my Br minus. He was a product from the previous step because again I did not add Br minus. I had to generate it from the previous step over here. So my Br minus is going to come into attack, And this is again like an SN2, the Br plus is taking up a lot of space on this side, so when the Br minus comes into attack, it's going to be a backside attack, because we're trying to avoid some of the sterics that could happen here. So he's going to come in from behind. I'm going to show the 2 electrons here going to the Br plus, and then just draw the product of that reaction. So that means I have 2 carbons here, my new Br is attached up here, the Br on the bottom is still attached to one of the carbons, just not the other, but now he's neutral. And again, with these groups, I can leave them the same. They're still dash wedged the exact same. I've just moved them down or up because of the way the other groups came in. So that's why I personally like to make it 3D before I actually show any attacks, because ultimately I can see a very clear example here where I received the anti-addition product. So I have the 2 groups anti to each other. And it avoids playing around with any sort of dash wedge after the fact, which again I find a little bit easier. The key thing with this that we have to keep in mind is that there's multiple pathways the molecules could take. So theoretically at the start here I grabbed my bromine, I had my bromine attack from the bottom, but the bromine could also attack from the top. So let's show that as well. I'm going to start with the same starting material here, and I'm still going to make him 3D. So that and that, but I'm going to have my Br on the top that I'm going to be using to attack. So let's get some lone pairs in here to make sure I can properly show all my arrows. So my alkene attacks, kicks out one of them, and the one I attacked comes back with another lone pair. And again, you can see it doesn't matter which carbon I show that attacking to, it doesn't make a difference. So that gives me an intermediate here, where the bromine still has 2 lone pairs and a positive charge, and the groups are shoved down a little bit to make some space for that halonium ion. But they're still the same stereochem, they're still the same dash wedge. So in this case, when my Br minus comes in, again I do have a choice between 2 of the carbon atoms. So you have 2 choices in how you could do this pathway. Either show attack from the bottom, show attack from the top, and then choose the same carbon to attack from with the Br minus. And that's what I recommend. It's not actually important in this particular example, but it is when we do the halohydrin. So if there's any reason that there'd be selectivity, then you have to show attack both from the top and bottom with the initial Br2. So in this case I showed attack from the bottom, and then I attacked the right carbon with my Br minus. Then I'm showing attack from the top with my Br plus on the top, and then I'm going to attack with my Br minus to the same carbon I did in the top example. Basically, we're always going to get 2 products from this. It's just which pathway you choose in order to get them. So I'm showing it attack the carbon on the right once again, and you'll see what happens here. I have my Br down there, my Br up here, and my other groups dashed wedged the same as they were before, only shoved up or down in order to make room for them. Now, of course, the key to this is they still look pretty much exactly the same. The only way to be sure that you've made 2 different products is to assign the RS. That's a really nice, clear way of doing this. So let's assign RS to the different centers and make sure we actually have 2 different products. So the substituents that I have here are all basically the same. So bromine would be the top priority, then this one, then that one, then my methyl group here. So if I look at the stereochem of that, it goes A, B, C, which is counterclockwise, but my lowest priority is facing forward, so I have to say instead of S, it's actually R. Same thing for the other one, 1, 2, 3, looks like S, but really my lowest priority is pointing up, so that's also R. And in the bottom example, bromine to that guy looks like R, but really is S. And same thing with the other one. Again, looks like R, but really is S. Oops. So, based on our RS's that we've assigned, we can see that those 2 molecules actually are different. You gotta watch for this. Sometimes you will generate the same thing. In that case, it could often be a meso compound. So if I didn't have the cis isomer to begin with, if I had the trans isomer starting material, I would generate meso compounds. But again, don't memorize this. Just do the different pathways, come up with the products, check RS to see if you've made different products. So here we have another reaction with H2SO4 and water, which we said before we know is H3O plus and HSO4 minus that we're not going to be using. So that means I have a nice strong acid in the presence of my alkene. So first step's going to be an acid-base reaction. and he's going to take a proton, kick out water, and at this point I have to decide which carbon gets the hydrogen, which gets the positive charge. And due to the structure, I'm going to put the positive charge on that guy, so he's tertiary. That means the hydrogen went over here. Now, I'm not too worried about this because I have a tertiary carbocation. I don't have to worry about rearrangements. So basically the next step's just going to be my, in this case, water attacking, my nucleophile attacking that center. And we've got lots of water kicking around. This is a nice dilute solution. So nucleophile attacks electrophile. And ask yourself, do I have to worry about stereochem? And because the two groups on either side are the same, I do not. So I don't get the product here, I only get an intermediate. And I know that because my oxygen has a positive charge if I followed exactly what I did with my electrons, which means I get a one bonus step where I deprotonate my intermediate here to generate the final product. And again, I don't have to show stereochemistry. If you do, that's fine, as long as you only show the one product and don't show multiple things, which makes it look like they're actually different when they're in fact the same. Here we have a nice alkene that's a nucleophile / base and super strong acid, HBr. So likely thing to happen here is again the acid-base reaction where my alkene rips off the proton from the acid because it's a nice strong acid. So I have the choice of where I put the hydrogen and where I put the positive charge. In this case I'm going to give the positive here, the hydrogen over here, so I don't have to worry about a primary carbocation. But I do have to worry about rearrangements because this guy is a secondary carbocation. So again, I can look to see if a rearrangement is possible. In this case, again, I can use my methyl group to shift over. So I take the electrons and the carbon and shift it over to the other carbon. Oops, that's no longer there. So this guy looks like that. He now has the positive charge and my methyl group is down there. So because of that, it means I have a new nucleophile to attack, but at least it's tertiary, so it's a little bit more stable. And I generated that nucleophile in the first step when I kicked out the Br- over here. So Br- is going to come in to attack that carbocation. And you got to watch for stereochem, but again, fortunately in this example, I'm not generating a chiral center, so that's going to be the one and only product. And I don't need to deprotonate anything because my nucleophile was negative to begin with. So for this reaction, we start with an alkene, and we have a two-step reaction with BH3THF in step 1, and the second one's got a peroxide, sodium hydroxide, and water. So the first thing I need to do is identify what type of reaction this will be. Again, it's going to be an addition, and if you recall from class, this is called hydroboration in the first step, and oxidation. And we did go over the hydroboration aspect of this before, and we covered a bit of the mechanism. I didn't show you the oxidation mechanism at all, but ultimately what are we adding? We're adding an H and an OH across the double bond, and it will be a syn addition, which is anti-mark. So the reason it's anti-mark is because our initial intermediate here, if I draw my starting material, my initial intermediate here is a BH3 type unit, so don't worry about too much what else is coming off of here, but the boron and the hydrogen both add at the same time to the starting material. So because of that, we're going to say that sterics plays a bit of a role here, and the boron will add to the carbon with the least number of carbons, and the hydrogen goes to the carbon with the most carbons. So right off the bat, because the hydrogen's going to the carbon with the least number of hydrogens, that's automatically an anti-Markovnikov addition. The rest of the mechanism involves switching the boron for an OH group, which happens in the second step, but again, we did not go over the mechanism for that. So I'm not expecting a mechanism here. I will just show basically when this first step happens, we get the boron added over here, the hydrogen added there, and the key thing we have to remember is the stereochem. So if my boron and hydrogen added to the same side, which they do because they come from the same molecule, then the methyl group that was there would have to be dashed behind. So let's do that. And then that means that because the boron I'm showing added from the top, there's no reason the boron could also not add from behind. So if it were to do that, then my BH unit would be dashed, my hydrogen would be dashed, which means my methyl would be wedged. So we're seeing two possible products right off the bat. The second part of the reaction involves the switching of the BH3 or the BH2 for the OH. So when we do that, it's important to keep in mind we just change them out, we don't change the stereochem. So if these two things were still dashed, they still are in the product, as well as for this guy. So here, that would be my OH, the H would be here, and my methyl would be dashed. So in this case, I do generate two different products. Check your stereochem to be sure. But they're not the same thing, so you have to show both products of this reaction with the stereochemistry. So for this reaction, it's another one you kind of have to memorize. First step is the oxymercuration. And second step is demercuration. So in this reaction, what we're doing is this is one of the three ways we know how to add water across the double bond. And it follows Markovnikov's rule. But the key to this is it does not have an issue with rearrangements. So, carbocation rearrangements. So, the benefit to this is if you have a molecule which would potentially rearrange if you just did the acid-water reaction, you could use the oxymercuration, demercuration to avoid that sort of rearrangement. In this particular example, it actually doesn't make a difference. We could have used the H2SO4 water to do the addition of the water following Markovnikov rule, but we put it under those conditions, so we got to know what they do. So basically, we're going to be adding water across the double bond. Because we're following Markovnikov's rule, then I know that the hydrogen goes to the carbon with the most hydrogens, oxygen goes to the carbon with the least hydrogens. This is not stereoselective, so it could add top or bottom. Fortunately for us in this example, that does not matter. So the product would look like this, and I don't have to worry about stereochem because it's not a chiral molecule or a chiral center. So that would be it. In this reaction, we have an interesting little reagent we use a couple times, the KMnO4. You'll notice this is a two-step reaction, KMnO4, base heat, and then an acid workup. The key thing to remember here with the KMnO4, it is an oxidizing agent, and we saw two reactions where we've used it. One where we have KMnO4 hydroxide cold, and the other with KMnO4 hydroxide hot. Either way, it does serve to oxidize, it's just the degree of oxidation that changes. So because we're under the heating conditions, this is oxidative cleavage, it actually breaks the double bond, and it's important to know exactly what it can and can't do. So for this guy, it breaks both CC double bonds and any CH bonds coming off of the alkene. So both of these will be cleaved and replaced with oxygen atoms, basically. So in our molecule, if I draw it out with the carbons and hydrogens shown, right, we have that, C, and I'm just going to abbreviate CH33, and over there I have two hydrogens. So given the conditions, I know automatically I'm going to be breaking that double bond, and when you do that, guys, just automatically break the double bond and replace it with a double bond O, double bond O. That's always going to be a given. The only thing hard about these reactions is recognizing what happens when I break my CH bonds, because all three of these CH bonds off the alkene will break. I do not touch the CH bonds over there, and I do not touch the CC bonds. Those are perfectly fine. So what happens is I either give it a single bond to oxygen or a double bond, and in this example, for the right-hand side molecule, right, this guy, when he breaks off, that's going to give me carbon, double bond, oxygen, and then this guy still has his 3 carbons, nothing's changed over there, but I've also broken off the hydrogen. So that's going to be replaced with an oxygen, and technically in the first step that would have been an O-, right, because I was still under basic conditions at the start here, but that's why we have the acid workup. The acid workup causes this guy to switch, and he'll no longer be negatively charged. He'd instead be an OH. So that would be the product on the right-hand side. On the left-hand side, the most common mistake I see with this portion is someone would replace both of these hydrogens with oxygen and draw me something that looks like this. C double bond O, that's perfectly fine, but then I would see something like this, where we have a double carboxylic acid. That guy has the right oxidation state, but he's not stable enough to form. So instead we form something a little bit more stable, so you're not going to draw us that, you're going to draw us this instead. So anytime you have a terminal CH2 like this, right, it's a carbon with 2 hydrogens and it's under extremely oxidative harsh conditions, the KMNO4 base heat, that guy breaks off entirely and forms CO2. So the two products of the reaction would be this. There are two products because anytime you break the double bond, unless it's a ring, you generate two different things in the process because it cleaves the double bond entirely. So for this particular reaction, again, we have the hydroboration oxidation, which we know gives us the anti-Mark addition of water, and he follows a syn addition. So anti-Mark means the hydrogen goes to the carbon with the least number of hydrogens. So in this case, that would be this guy, because he only has 1 hydrogen, whereas the other carbon of the alkene has 2. So basically what I have to recognize is it is a syn addition. In this case, it actually doesn't matter because the hydrogen's going to a carbon that already contains a hydrogen, and the oxygen's going to a carbon that already has 2 hydrogens. So either way, I'm not creating a chiral center, which means my product would look like this. OH over here, which is the anti-Mark product, and again, I'm not showing stereochem because I do not have to, but that would be the only product of this reaction. So for this reaction, we have an example where we're doing another hydrogenation, but our hydrogen source is actually an ammonia. It can also be a primary amine. And we have sodium present, which is a dissolving metal. So basically, you have to recognize what these things can potentially do. Here we're starting off with an alkyne, and we don't have a terminal hydrogen off the alkyne because it is substituted on both ends, which means I couldn't even depronate it. So really and truly the only thing I could do here was an addition, which means I just have to look at the reactants to see what type of addition I'm going to be doing. So because this is a dissolving metal sort of catalyst, we're actually going to get the anti-addition of the 2 hydrogens, and again the hydrogens coming from the ammonia. So it stops at the alkene, which is nice, and that means the 2 groups that were already on there will become trans to each other, and the hydrogens that I've added are also going to be trans. So this is the anti-addition of water, or sorry, anti-addition of H2 across the double bond. Stops at the alkene. Things to note about this: make sure you change your bond angles when you do this, right? Because we have changed the hybridization. So make sure it looks like an alkene afterwards. And that's basically it. He's just one more to memorize. So for this one, we have another alkene with bromine in the presence of dichloromethane. Again, dichloromethane is not reactive, so it's a simple bromine addition across the double bond, which we know gives us the anti-addition. And we got to watch stereochem because there's often a mixture of products. So what I'm going to do, as before, I'm going to make this into 3D first, because I find that makes things a little bit easier for stereochem. This one's not so bad, but it's good practice just to make sure we're consistent. So hydrogen's there, hydrogen's there, hydrogen's here, which means my bromine could attack top or bottom. So let's do this attack first. Lone pairs around these guys. Always a good idea to draw your lone pairs. We will ask for those in a mechanism. So these guys attack, that guy goes back, and that gives me a bromonium ion on the bottom. The 2 lone pairs, positive charge. I'm going to stop showing the hydrogens just for simplicity, because it doesn't matter. But there we go. Actually, no, I won't. We'll keep the hydrogen here at least. And why not? Keep the hydrogens over here. So there's my intermediate. Because I generated Br- in that step, that means my next Br- can come in. At this point, it doesn't actually matter, but I will do it just for simplicity and to make sure we do the same thing with the halohydrin. But I could attack, in theory, either of these carbon atoms, and I'd still get the same mixture of products in my final material. Because the Br- is the good nucleophile, he's actually more attractive to this carbon because that more closely resembles a carbocation, which we'll discuss with the halohydrin. So for consistency, I'm going to show that Br minus attacking that particular carbon from this intermediate to give me this product, where I have a Br up, Br down still attached, and the two hydrogens here, dashed and wedged, which don't really matter. And these ones just move down a little bit, even though that's fine. So there we go, that's one possible product. I want to show the other pathway as well, where instead of attacking from the bottom, my Br minus attacks from the top. So drawing this again down here, making sure I'm nice and clear with my two pathways. I'm going to show that. Hydrogen, hydrogen, and Br2 on the top with some lone pairs, so I can use those to attack. So nucleophile attacks, kicks out leaving group, and one of those donates back, which gives me an intermediate that looks like this. So the Br is now on the top, which is something different, believe it or not, though it looks pretty much the same. And these guys are down here, this guy is down here, and that means when my Br minus comes in, because this is like an SN2 in a way, I want to make sure I do a backside attack, but I am, for consistency, attacking that same carbon atom. I'm being selective here, because this more closely resembles the carbocation. And that will give me bromine up here still attached, bromine down there now attached, this guy dashed, and that guy wedged up as a hydrogen, and these two still dashed and wedged. Doesn't matter if you switch the order here, right, because this one was dashed, this was wedged, this is still dashed and wedged. So that's one of the other possible products. And again, we want to make sure that we did create two different products, so I do suggest doing the RS for those chiral centers. So to do the RS, we only have one chiral center to be concerned about, and it's this guy over here. The one on the left has two hydrogens, so I did not create a chiral center there, so I don't have to worry about that one. So let's make sure that we did two different things on the right-hand side. The bromine would be our top priority here. Our second highest priority would actually be this group over here. If you order things, then the carbon here is attached to a bromine, two hydrogens. The carbon here is attached to three carbons, so that is the first point of difference. So this guy would be C, hydrogen would be D. ABC looks counterclockwise, but because the lowest priority is up, looks like S, but actually would be R. And doing the same thing on the bottom one, A, B, oops, C, D, looks clockwise, actually is counterclockwise, so that's actually S, which is good. That means we generated two different products from this reaction, and if you follow the same way we did these pathways, you can never go wrong. You'll always generate two products if there are two products. Just make sure that you check the stereochem at the end, so that if you actually created the same thing twice, you're aware of it. So always check your stereochem when you're doing these reactions. For this reaction, we have, again, oxymercuration, demercuration, which we know gives us the mark addition of water across the double bond, and it's not stereoselective. So, looking at our starting material, this isn't a big deal. It's pretty symmetrical, which means it's pretty straightforward addition. So with my double bond here, really it doesn't matter. You can't get a marker anti-mark with this because it's symmetrical. So basically all I have to do with that is add an OH and an H. And whichever carbon I add a hydrogen to, because it already has a hydrogen, I know that's not going to generate a chiral center. So really, I just need an OH. Do I have to show stereochem? No. Are you wrong to show stereochem? No. So if you want to show that, or make it dash, that's fine, as long as you recognize it's the same thing and don't draw it twice. So with or without stereochemistry is fine, because I don't have a chiral center. So no chiral center in this example. And that is it. Another fun bromine addition in dichloromethane. So I'm going to take my starting material, dash and wedge, making sure I keep the same group cis trans to each other. So there we go. And if I do bromine addition on the bottom, like so, I get my first intermediate, so he attacks, he leaves, he attacks back, which gives me, oops, 2 carbons there, brominium ion on the bottom, 2 lone pairs positive, keep all this the same, oops, that was a ethyl, and keep that the same, and the hydrogen's behind. Good. And when the Br minus comes into attack, again, always make sure you attack from the opposite side as the halonium. So he has to come in from behind. Again, to be careful here, I want to be selective, so I'm going to attack the carbon with the most carbons coming off of it, because that's what I would do with the halohydrogen as well, and that won't lead me astray. So if I attack that carbon, then this guy gets kicked up, and we get a nice clear evidence of the anti-addition. And again, all I do is shove this guy down to make space for him, and my methyl group would be up there, and the hydrogen would be behind. But that's not the only product. We have to show the other possibility where the bromine was added from the top instead. So keep the stereochem all the same here so you're not duplicating things. So then my lone pairs, he attacks him, he gets booted out, he comes back to attack, which gives me the bromine on the top now. Again, 2 lone pairs, positive charge. Keep these the same, just move them down so we have more space. So then when the Br, that is a really messy positive, when the Br minus comes in, has to attack from the back, and for consistency I will attack the same carbon atom. So again, I'm attacking the more substituted carbon atom here. So I keep things consistent, which would form Br down there, Br up here. This stuff gets shoved up, but still retains the same stereochem, like so. And those are my 2 products. We still want to make sure we actually generated 2 different things in this case, so let's assign some RS. In the top example here, bromine's the highest priority, followed by this and this and this. So ABC looks counterclockwise, but actually I know it should be R. 1, 2, 3 for the other guy, pretty straightforward, he's S. And on the bottom one, 1, 2, 3, that guy looks like R, but actually is S. 1, 2, 3, that guy is R. So we see RS, SR, and some of you may consider this to be a meso compound, and that is something that you want to be crossing your mind. But in order to be a meso compound, we have to have 2 or more chiral centers and an internal mirror plane. So in this case, we do have opposite chirality, which is a good sign for a meso compound, but this carbon over here has a methyl and an ethyl, and this one just has the methyl. Right, so I can't have a meso compound if I don't have an internal plane of symmetry. In this case, I could not have an internal mirror plane because I don't have the same substituents. So there actually are 2 different products here, and the 2 different centers have 2 different chiralities, so I did this correctly. Here we have another oxymercuration demercuration, which we know follows Markovnikov rule, and it's with the addition of water to form an alcohol. And for that, anti-mark, yep, and it's not stereoselective, so we got to keep that in mind. So looking at our problem here, we see that we have a carbon with 2 hydrogens versus a carbon with 1 hydrogen on my alkene, which means if I follow Markovnikov's rule, my new hydrogen will be adding here, which means my OH will be adding here. So preemptively, this looks not too bad, but that does mean that I am going to be generating a new chiral center afterward. So I do have to watch for chirality. This is non-stereoselective, so that means that both addition from the top or bottom could happen. So that means I actually get 2 different products from this reaction. But the benefit to this, as compared to the water-acid one, is that I do not have the possibility of a rearrangement. So here I can form a secondary alcohol without a rearrangement occurring. I just have to keep in mind that I will get different stereochemistry based on the addition. So in this case, I ended up with the S chirality at the center, and this one would be the R chirality. The hydrogen also added, but I don't have to show it because it's a given that there's 3 hydrogens now on my methyl group on the terminal end. So both products are possible. I would have a racemic mixture, which means racemic mixture, which means the products of the reaction would not be optically active because it'd be a racemic mix 50-50 of the 2 products. So another bromine addition, and we have 2 possibilities, either from the top or the bottom. So in this case I have one methyl group wedged, the other one dashed when I make that into 3D. So when I have my bromine come in to attack, top or bottom can occur. I'm going to show both pathways, make sure I don't miss anything. So in that case, I have methyl group wedged, methyl group dashed, and then my bromine down here. And I always do that where there's not much space on the top. But you know what I'm doing. Br minus is going to come in. And in this case, there's definitely no reason to be selective. Both have just one methyl group, but I like to attack the one on the right for some reason, so let's do that. So I attack the one on the right, which means the bromine here is now attached. This guy is still attached down there. This guy just got pushed down, and that guy's left up. And we gotta do the alternative as well. So have the bromine on the top when he attacks with all of his lone pairs. So he gets attacked, that guy gets booted out, and this guy attacks back, which would generate an intermediate that would look something like that. Br on the top, 2 lone pairs, positive charge, and methyl group, methyl group. So when my Br minus comes in to attack, again, always attacks from behind. For consistency, let's attack the carbon on the right once again to make sure I don't get the duplicates necessarily. And that means bromine here is still attached, bromine there is still attached, but that guy is pushed up, but still retains the dashed chemistry, stereochem. And those are the 2 possible products. But we got to make sure we didn't create the same thing twice, so let's assign some RS. Top one we go A, B, C, and the hydrogen would be D. So looks like S, but actually is R. This guy is S because the hydrogen's already behind. And the bottom structure looks like R, but really is S. And that one actually is R. So we have SR, RS, but you may notice that the groups coming off of each of those chiral centers is identical. We have a bromine, a methyl, a hydrogen, and then the other thing. So if I were to do a rotation here, perhaps, rotate around the double bond here, you would see something that looks like this. Bromines would both be up, and these guys would now be wedged together. Does anybody recognize what that is? That's a meso compound. RS, internal mirror plane, that's meso, which means I can do the exact same thing with the top structure, which means these are both the same molecule. So that's important to notice. We've generated the same thing twice, so if I was asking this as a synthesis, I would only draw one as the answer. So this would be the answer to the reaction. You only draw it once. If you draw both of them, then it looks like you think they're different, and we just established that they're actually the same. So it's one compound, it is a meso compound, which is why we were able to generate it twice. But check your chirality, check for connectivity to make sure that that is that you recognize that that's a product of the reaction. Alright, another water acid example, which means we have H3O plus and HSO4 minus. So mechanistically, we got this guy with 1 lone pair and a positive charge. Alkene attacks him because that's an acid-base reaction. We get the carbocation on the central carbon to make sure it's tertiary, so no rearrangement worries. Then water's going to come in to attack that guy. I feel like I've done this before. But there we go, water is attached, but that means that he then has a positive charge we got to take care of. So I'm going to use another molecule of water, not the conjugate base of the sulfuric acid, that's not a good base. So we get a final product that looks like this, and again, don't have to worry about stereochem because they don't have a chiral center. Here again we have an example of a poison catalyst, which is a dissolving metal. So we've got the lithium here, and that's our hydrogen source. And as we said earlier, we know that this gives us the anti-addition of hydrogen to an alkyne or an alkene. So in this case we do have an alkyne to start off with. So I have to recognize that one hydrogen will add to the bottom, the other hydrogen will add to the top, which gives me a product that looks like that. So hydrogen, well, that looked confusing, but hydrogen top and bottom, so I end up with the anti-addition of the hydrogen. which often will give us a trans product. Because we have two other groups there, they're automatically going to go trans. Here's a new one. We have KMNO4 hydroxide cold, which is a very important factor. So again, we have two reactions where we use KMNO4, but the condition of cold and hot is the only thing that differs. So in this case, because it's cold, I know that's actually the diol formation. So I don't break entirely the double bond, and I don't break CH bonds. So for diol formation, I know it's a syn addition. And the logic behind that was because the two oxygens come from the same molecule. And I showed something in class, and basically it was just to give you the idea that the two oxygens add from the same molecule, so it's going to be a syn addition. So looking at my starting material to do the syn addition, that means my two alcohols will end up on the same side. And for this case, I am going to be generating chiral centers, so I want to make sure I keep the stereochem the same. So ultimately I'll have a product that looks like this, but let's just take it back a step and make this into 3D to see where that came from. So basically if I rotate this guy towards me, I would have a methyl group towards me, ethyl group tashed, methyl group towards me, ethyl group tashed. So important thing to note here is I still have the syn or the cis product. So then when the diol forms, the two oxygens can add to the same side, right? But there's no reason why they can't add top or bottom. So if I add from the bottom, I will get the product I showed over here, or if I add from the top, let's just draw that again, like so, right? Two OHs can add from the top as well, which would give me that, and those would stay the same, right, dashed and wedge. So again, thing I want to check here is make sure, are these different things or are they the same? So in this case you can assign chirality if you'd like, or hopefully you can visually see that if I pick this molecule up and rotate it by 180 degrees, it would be the exact same thing as this one. So in this particular case, this is not a different product. And if I asked what was special about these products, you may note that they're meso. So here I have, looks like R but actually is S. This guy's R. And again down at the bottom looks like S but actually is R. So although I did flip them over, they are still the same molecule because they do have an internal mirror plane running down the center and have two or more chiral centers. So I generated two different meso, or I should say two meso products, but that means they are actually the same thing. So there's only one product of the reaction, so make sure you only show one if we're asking this as a synthesis. Here's a fun little reaction called ozonolysis. Ozonolysis. And it's oxidative cleavage, where I break the double bond, but it's not as harsh as the KMNO4 one. So the KMNO4 with the heat, that one's a lot harsher and it actually breaks CH bonds, whereas this one does not break the CH bonds off the alkene. So leaves those intact, which means I get aldehydes and ketones as the product of these. Aldehydes and ketones. So I do break the double bond, that's the first thing I notice, and with this all you have to do is cut down the center and replace the double bond with a double bond O on both sides. So all I'm going to do for this is just draw the ring a little bit bigger so I know that I broke it open, and double bond O, that's it. I leave this intact because this is not strong enough to break those CH bonds. If it was KMNO4 hot, it would. But that means I only have one product of this reaction, and if I draw it out in full and draw it out a little bit longer, 1, 2, 3, 4, 5, 6 carbons total, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and on carbon 2 I had the double bond to oxygen, and on carbon 6, double bond to oxygen. Either way of showing it's perfectly fine. You know, if you don't want to take the chance of unspooling it from the ring, that's totally fine as long as your bond angles aren't too bad. And you have the right number of carbons and the oxygens are in the right place. But again, in this case, my CH remains intact, so I get an aldehyde from this. And this particular example, I also had a ketone on the other end, but one molecule from that starting material. So looking at my starting materials and reagents here, we have to figure out what type of reaction is going to happen. Again, we've got our alkene, which means I have a nucleophile / base, and we've established this guy is just a solvent, and it doesn't participate in the reaction, which is fine. So the only other thing I have is Cl2. Cl2 is still kind of reactive, not as reactive as the bromine, but he still can become polarized in the presence of electrons to become a delta plus and a delta minus, which means I've got an electrophile and a leaving group. So based on that, I can do the same sort of chemistry I was doing with the bromine. So again, that means I'm going to take this guy and make him 3D just to make sure I don't miss anything. So he'd be wedged and he'd be dashed behind. I'm going to not show the hydrogens for simplicity. So then my chlorine can attack top or bottom. Oops, not bromine. Chlorine. So show all your lone pairs to make sure you get everything there. So he attacks, kicks out the other Cl, this guy attacks back, which gives me an intermediate that looks like this. And yes, chlorine is capable of doing this. He's still large enough to make it happen. Fluorine, however, is not reactive towards these type of reactions, so you'll never see F2 do this or I2. So it is selected to Cl2 and Br2. But the chemistry of it is the same, so then my Cl2 will come in, or sorry, the Cl minus will come in to attack. In this case, the two carbons are basically the same with what I'm going to do here. I'm going to attack the one on the left because it's got an ethyl group versus the methyl group, but doesn't really matter in this case. So I'm going to attack him, boot him up. So I end up with the anti-addition of the chlorines. This guy would be wedged, that guy would be dashed. But we know that there's two possible ways this could have happened, and there's no reason it would have been selective, so my chlorine could also have attacked from the top. So we're going to show that as well. Him getting attacked, him getting kicked out, him donating back, which gives me the other form of my intermediate, which is different. So that's still wedged, that's still dashed behind, that's my ethyl group. So when my Cl minus comes in, again I'm going to attack the same carbon as I did in the top one, so the left one over here. Got to be consistent so I don't generate too many things. And that leads to the anti-addition there, two chlorines, and he's still wedged, he's still dashed. Once again, we want to make sure that these are the same or different. So if we assign some stereochem going around there, that would be R. This guy going around looks like R but actually is S. And same thing on the bottom, that's S and that's R. So good, we switched our chirality. Oh, notice something significant missing there. That should be an ethyl group, not a methyl group. Because if it was a methyl group, then we'd have a meso compound. But because the connectivity here is different, we do not. So it's not meso, there are two distinct products to this reaction, and you would have to show both of them. Here's another hydroboration oxidation, which we know gives the water addition, and he gives an anti-mark product that is syn. So we got to keep all of that in mind. So with that in mind, actually, let's take this into 3D. So we don't have to worry about the stereochem of what we're adding. So if I were to do that and add my BH unit and my OH, ultimately I know that the hydrogen here will go to the carbon with the least number of hydrogens, which would be this one. So my hydrogen will end up going here, and my oxygen will end up over here. So if I write the products of that reaction, I would have OH down here, hydrogen down here, ethyl group pushed up, methyl group pushed up, but the stereochem remains the same. So the syn addition can also happen from the top, not just the bottom, which means I could redraw this stuff here, but show the oxygen adding from the top and the hydrogen from the top, which can potentially lead to different products. In this case it does. So the hydrogen's up there, methyl group is wedged, methyl wedged, ethyl dashed, and those are the two possible products. Again, always want to double check and make sure you've made something different, but because we have chiral centers on the carbon adding the OH group, we know that they will be different products based on the stereochem. So in this particular example, we actually generate two chiral centers. Both places of addition are chiral, and we want to make sure they're different, so again, assign your RS and you will find that they are two different products. So for the RS on this guy, we have OH and then the other group and then the methyl group. So that guy is S, and what he's attached to is a little bit more challenging. You have to picture yourself looking at it from the top here, because the hydrogen's the lowest priority and he needs to be behind. But if you do that, we end up with R, and for the other two, we end up with R and S. So two different products. Once again, the connectivity is completely different, so we have no chance of a meso compound, but you have to note that the two change, which means, how are these two things related? Well, they're enantiomers. So play around with that if you want, make sure you can see it, but they would be non-superposable mirror images, and we know it because the two chirality centers have changed. So for this guy, it's a little bit different. We have Br2 again, but you'll note the solvent isn't CH2Cl2. We've got something a little different here. This is ethanol, and ethanol can be a competing nucleophile because you've got lone pairs on that oxygen. So we got to watch out for that to see how that might change the reaction, but it is definitely not an electrophile, so the first step of the reaction is still identical to the regular bromine addition. So here I'm going to again make him into 3D, just to make my life easier later. So my two methyl groups are on the same side, ethyl group behind. That means when my bromine is attacked, because again, that's my only electrophile I've got kicking around, so that makes sense, that's going to happen. I attack him, kick him out, attack back to get my bromonium ion on the bottom, based on how I've shown it here. So he's there, and methyl group's there, ethyl group's back, and methyl group's wedged. So at this point, because we have this really good electrophile, virtually anything nucleophilic can attack. So we have two options. We have either ethanol or we have the Br- we made in the first step. So Br- is definitely a better nucleophile than ethanol, but we don't have much of it, whereas ethanol is the solvent. There's tons and tons of water molecules, millions of them. Sorry, not water, ethanol molecules. So odds are ethanol is more likely to come into contact with this intermediate than the bromide would. So the second step of this mechanism involves the ethanol attacking. So that's one aspect we have to think of. The other one is the fact that we have two carbons that this guy could attack, and they are different. So here I have a carbon with an ethyl and a methyl, here I have a carbon with just a methyl. So because this guy is more substituted, he more closely resembles a carbocation because he can handle the charge better that would be being distributed from this bromonium ion. So basically this guy can handle more of the positive charge, so he resembles a carbocation more than this one will. So we do have selectivity here. This is regioselectivity because my OH from my ethanol will be selectively attacking the guy on the left. So he's going to attack that carbon in this step, which will give me, again, the anti-addition. Still is anti. But I'm not done because there's still a hydrogen attached there. So this group is up, this guy gets pushed down some, but the stereochem stays the same. And then I need one more step here to deprotonate because that's not stable. So another molecule of ethanol can come in to do that with his lone pairs. It's getting kind of messy, but there we go. He can deprotonate, everything stays the same stereochem-wise, but we get kind of a unique product. So there's my methyl, there's my ethyl. Now, because we have two different pathways we can take on the first step, we have to show both. And here, my starting material would be the same, but my bromine can attack from the top instead of from the bottom, and that'll generate a different intermediate. So I get bromonium on the top, two lone pairs positive, this guy's there, that guy's there, and the ethyl group's there. So when my ethanol comes into attack, always backside attack, right? It's kind of like the SN2, but it's SN1 because it looks like a carbocation, so it's kind of in between. but that means he's selective. So he'll regioselectively attack that particular carbon, which gets me to that intermediate, which has one lone pair positive charge but is anti to my bromine, where I've got a methyl group there, and ethyl group there. And another ethanol comes in to deprotonate that intermediate, which gives me anti-addition, which looks like that. This guy stays the same stereochem-wise. And there we have it. Two different products. Sign RS just to be sure. So on the top structure, this would be R. Oops, change color. That would be R. And this guy would be 1, 2, 3. Looks like R, but actually is S. And then these are the opposite. That would be S. And that would be R. So two different products from the reaction. This is kind of like a halohydrin, but I don't call it exactly hydrogen because it's not water, it's ethanol that we're attacking instead. So any water or alcohol can do this. And they can do it with either Br2 or Cl2. So watch out for that on the final. Once again, we've got some permanganate here with KMnO4 and heat, which tells me this is going to be the oxidative cleavage, not the diol formation. So what that means is I'm going to take my double bond and I'm going to break the CC double bond, and I'm going to break any CH bonds off the CC double bond. So that means here, 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 and here. So as we saw in an earlier example, the molecule on the left, the carbon-carbon bond remains the same. I just double bond, the double bond goes to become a double bond O, and the one on the left, my hydrogen bond is now replaced by an OH bond, and the hydrogen here comes from my acid workup. And on the right-hand side of the molecule there, we've got the C double bond O, again from that left-hand side of the double bond, but I broke both my CHs to result in the more oxidatively stable C double bond O, so CO2. As opposed to making two single bonds to oxygen, we make a double bond because it's more stable. So those are the two products of that particular reaction. And here we have Cl2 with water. Again, Cl2 is a potential electrophile, this guy's a potential nucleophile. So I'm going to convert him into 3D because I know stereochem's going to be tricky for this one. So methyl groups are forward, ethyl groups back, and my chlorine could attack from the bottom. So we'll show him first. So he gets attacked, he kicks that guy out, and we donate back to get the first intermediate, where we've got chlorine down there, two lone pairs positive, that guy's wedged up, that guy's dashed back, like so. And at this point, again, we have to reassess to say what nucleophile will attack this electrophile. Once again, our two options are Cl- that we generated in the first step over here, or water. But one of those is in excess, the other one is not. So odds are water is going to be our guy to attack at this point. And water has a choice. It could attack this carbon or it could attack that carbon. And because he's not such a good nucleophile, he will attack whichever carbon represents the carbocation most. And that means it's going to be this guy, because he's more substituted. So water will be attacking that guy, like so, and breaking the bond up to the chlorine is the leaving group, which means I get OH2 up here with a positive charge. Chlorine would be down there, methyl group up, and methyl group and ethyl group down there. So we're not done. Another molecule of water is going to come in to deprotonate. Remember to use water, not Cl-, because that is never a base. And that gives me my final product over there. But once again, gotta watch out for other pathways. So instead of doing that, we have the other option where the chlorine came in from the top, not the bottom, like so, which means this guy gets attacked, that gets booted out, and this comes down again, which would generate the other intermediate, another halonium ion, and then it's got a positive, So when the water comes in, he'll attack from the bottom this time, because it's always opposite, but he will still selectively attack that one carbon atom, because that more closely resembles the carbocation. So we get this, I am getting messy, and chlorine, methyl group there, that's attached, ethyl group, methyl group, another water molecule used to deprotonate, like so, which gives me OH down, chlorine up, methyl, ethyl, and methyl. And these are two different products. Check your RS just to be sure. That is R. That is, looks like R but S, which makes this guy S and R. So two different products of the reaction. You'd have to show both in a synthesis and a mechanism. Once again, we have our friend KMNO4 with some heat, which means oxidative cleavage. And we've got the acid workup, which means any acids will be protonated. Protonated. I can't spell. Tonated. Wonderful. So we're going to break our double bond in half and replace them with oxygens. So if I draw this out a little bit bigger, that means that this guy gets broken, and I just replace those with oxygens, double bonded oxygen, and my CH also gets broken, and I replace that with an oxygen as well. So that would give me a really stretched out ring if I want to draw it that way, because I'm lazy. There we go, double bond O, but this is no longer an H because we can't get aldehydes, so it's got to be a carboxylic acid. To be sure you did this right, please count your carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that's fine. Once again, if you want to draw it out linear, no problem there. Just make sure you count your carbons so you did it correctly. So this reaction will always give ketones and carboxylic acids, but never will give aldehydes because we break those bonds. So aldehydes are not possible with this one. And we're back to ozonolysis, which is very similar to the last example, except we do keep the CH bonds of a double bond. So this guy here and these guys are perfectly safe now because we're not under the really harsh conditions. So when I break it, again, just break your double bond, replace that with a double bond O, and that's it. So this guy would give me C double bond O with 2 hydrogens still attached, because I don't touch those. And the other half would give me a C double bond O with a hydrogen, and then a C with a bunch of CH3s. Make sure you count your carbons so you didn't lose any in the process, but I think I'm fine. So this guy, again, gives aldehydes and ketones. And because it's one molecule that wasn't connected, I get 2 molecules when I break it apart. Another ozonolysis. So I'm going to break my double bond. Let's make him a little bit bigger so I can see it. So break my double bond in half, but keep my CHs. So I just literally break that, replace it with double bond O, replace it with double bond O. And if I draw that all stretched out, then it would look like this. Here we go. Double bond O to that, double bond O, and that hydrogen is still there because this is the weaker form of the oxidative cleavage. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Good. So I didn't lose any carbons in the process. I ended up with aldehydes and ketones, which is what I was expecting. So probably did it right. So this little guy is a reagent we've seen only once, but he's meant for diol formation. And we can form diols a couple different ways. One is the OSO4, the other is the KMNO4. But we know it's always a syn addition, which is important to keep in mind. And we don't need to worry about the mechanism. I did show that they come from the same molecule, so both oxygens are from the same starting material, the same molecule, which explains the syn addition. So really, I'm going to have 2 oxygens adding to the same side of the molecule here, or it could also add from the top, so you got to keep that in mind if any stereochem is an issue. For this example, I don't think it actually is, so if I draw that guy out, I would add an OH and an OH, and I'm right, there's no chiral centers, so that's perfectly fine. I'm going to draw that a little bit better. 1, 2, 3. So OH and OH and a methyl group. Yeah, that looks a little bit neater. But doesn't matter, it's a syn addition, and top or bottom in this case would lead to the same thing. So I don't have to worry about showing the stereochem, and that would be the only product. Here's another example with a syn addition. In this case, this is going to make a big difference if I show stereochem properly. So from my starting material, again, the OHs can add top or bottom to this guy, so I have to show both. If the two OHs added both from the top, then they would both be wedged, but that would push my methyl group here dashed, and the hydrogen would also be dashed, but that's a given, I don't have to show. Or the other route would be that they both come from behind, which means they would both be dashed behind, and my methyl group would be dashed, or wedged forward. So in this case, they are generating two different things. You got to watch for your stereochem. So this would be S, that would be R, and that would be R, and this would be S. So I generate two different products from the reaction, and they're different. So we got to make sure to show both in a synthesis or a mechanism. Here we have KMNO4 again, but he is cold, which means I'm going for the diol formation. So same as the last example, I can add either both oxygens from the top or from the bottom, and that will lead to two different products, so I have to make sure that I keep my stereochem in mind. So in this case, if I added the two OHs from the top, let's say, then that would push my methyl group behind, and in this example then my hydrogen's in the plane. Or, that's not going to be an arrow, or I could draw it the other way, where my OHs are both dashed, which would make my methyl group wedged, and my methyl group wedged, and the hydrogen still in the plane. Perfectly fine, either way you draw it, it doesn't really matter as long as you check to make sure your stereochem was done properly. So you want to make sure that you have RS done well and that they have made different products, and that you've kept the syn geometry. That's by far the most important thing. So here that would be R, I believe. So he would be 1, 2, 3, that'd be S. 1, 2, 3, that would be S as well. So there we go. I made two different products from the reaction. You can draw this any way you like, but for simplicity, I would always make sure that you just keep the syn geometry in mind. So make both wedged, both dashed, or both in the plane, doesn't matter. You're welcome to change this into 3D first and then do the addition. Again, whatever way you like, just make sure that you check your stereochem to know that you've done it properly. So here again, I have two products. And last question, we have a hydrogenation, H2, in the presence of Lindlar palladium. And that is a poison catalyst, which gives us a syn addition, which we just have to know. So that means both hydrogens will be adding to the same side of my molecule. And we do have control over this to know that we can stop at the alkene. So if I'm just saying I had one equivalent here, then I can stop at the alkene, which means I would get that as the product. And top can also happen, right? The two hydrogens could add from the top, but you have to recognize that that is the exact same thing, so there's only one product from the reaction. So you should only show one. So don't show me both, just show me one. That's it. So hopefully you found this beneficial. Lots of practice is obviously the best thing, so take your time, go back, pause the tape whenever you'd like, and yeah, hopefully it was helpful.